Okay, so hello and welcome to this video tutorial for A-level mechanics. So we have this problem from the June 2023 paper here. I'm not going to read out the question to you guys because I trust that you've read it all yourselves. So part A is kind of a conceptual problem. It's asking, state the direction left or right of the frictional force acting on the rod at A. Give a reason for your answer. So I can already think of two reasons why this is acting to the right. I suppose one reason is to say that the frictional force is acting to the right to prevent slipping. So in our answer here, we can say right to prevent slipping, something like that. Or alternatively, we could say to counter normal, apologies for my handwriting here, normal force at B, something like that. It describes later in the problem here the magnitude of the normal reaction of the wall on the rod at B is S, so we can add that to our diagram here. We can call that, we're calling this down here F and we're calling this up here S. Okay. So this is S here and this is F. So you can see how the rod is in horizontal equilibrium, right? F is counteracting S here. Okay, so part B is saying by taking moments about A, show that S equals a half mg cot of theta. So naturally, we'll want to add to our diagram here. What do we want to add? Well, there's a force that we still need to account for here, M, which is the weight of the rod, i.e. mg here. And we can add some geometry to this diagram here. So it states here that the rod AB has a length of 2a. So we can add that to our diagram here. We can say this rod has a length of 2a. And since the rod has a length of 2a, we can say that it's kind of got a horizontal component of 2a cos theta, and that it's got a height of 2a sine theta. Right? Cool. This is everything we need. Let's go ahead and take some moments about point A here. So we can say the sum of moments at A acting clockwise or anti-clockwise, doesn't matter, is equal to 0. So that's basically saying the moments acting clockwise are equal, or at least their magnitudes are equal to the sum of the moments acting anti-clockwise. Let's take the moments acting clockwise first. So if I'm imagining I'm kind of pressing my finger down on point A here and imagining which forces are moving the paper or the diagram clockwise, well, we've got this mg force here, right? Now, since we're taking this length as 2a cos theta, we can almost take this length, which I'm taking as the midpoint here, assuming this is a uniform rod. I don't know if it states that in the problem, but it's a sensible thing to assume. Uniform, there you go. This length here must be a cos theta, since this entire length is 2a cos theta. Let's just add that in there, a cos theta. So this moment here can be taken as, let's say, mg a cos theta. Since a moment we understand to be the product of the force and the perpendicular distance from the point of interest. Things acting anti-clockwise then, well, we've got this normal force here. That is 2a sine theta away from point A, in a sense. So we can say S 2 oh, that's not a very good order, is it? Let's say 2s a, doesn't really matter, sine theta. Okay, one thing that we can immediately notice about this is that you've got an a on both sides. We can divide through. And we're looking for s here, so let's rearrange for s. We can do that by dividing both sides by 2 sine theta. So we can say, therefore, s is equal to a half cos theta over sine theta mg. Therefore, s is equal to a half cot of theta mg. Okay. Awesome. Let's move on to part C then. So part C is asking us to determine the value of mu here, where mu can be taken as the coefficient of static friction, where static friction is the product of the coefficient of static friction and the normal force. So it looks like we need to add another force to our free body diagram here, which is this. Let's call it n for normal force here at A. Right, so we're trying to find mu here. We have a bunch of unknowns, but we can also determine a bunch of relations. And this is something I always like to emphasize to my students, is this idea that if I have as many unknowns as I do independent relations, the problem is typically solvable. This is why simultaneous equations, in a sense, are solvable. If I have 2 unknowns and 2 equations, the problem is solvable. Okay. Let's just state a bunch of relations, including all of our unknowns here. We've got n, we've got f, we've got s, we've got m. We've got 4 unknowns there by the looks of it. And a, but I don't think we need to include a here. So we have this s equals a half cot mg, but the question notes tan of theta is equal to 3/4. I trust that you guys will understand that that means that cot of theta is equal to 4/3, since cot of theta is just the reciprocal of tan of theta. We can say, therefore, s is equal to, well, a half times 4/3, that's 4/6, that's 2/3, 2/3 of mg. Okay, we've stated that. What else can we state? Well, we can consider the vertical forces acting on our rod here. We've only got n and mg. N and mg must be equal to each other if this is in vertical equilibrium. So we can say n is equal to mg. We're already getting somewhere here. Let's consider the horizontal equilibrium. Well, we have s acting. We had f acting to the right, s acting to the left. Therefore, f is equal to s. What else do we have? We have the fact that our frictional force here is equal to our coefficient of static friction, which is what we're looking for here, times the normal force. So we can say F here is equal to mu n. Okay, so we have S. I'm counting the number of unknowns we have here. We have S, we have M, we have N, and we have F, and we have mu. Okay, we have 5 unknowns by the feels of it. Let's do a bit of substitution. So we understand that n is equal to mg here. So we can say that we can substitute mg in for n. We can say f is equal to mu times mg. We're noting here that f is equal to s, so we can say that s is equal to mu mg. Note here, we're saying here s is equal to 2/3 mg. Here we're saying s is equal to mu mg. We can say therefore mu is equal to 2/3. Okay, which we can approximate to 0.67 if you want to give it in a decimal form. Okay, let's move on to part D then. So part D is asking, find in terms of M and G the magnitude of the resultant force acting on the rod at A. So in a sense, we want to kind of hone in on point A here. We want to just consider point A. Let's go ahead and do that then. We understand there are two forces acting at point A here, this normal force N and this frictional force F. Let's diagrammatize that. We can say we've got force N and force F acting here. We've noted in the previous question, N is equal to mg. F is equal to mu mg, and we determine mu to be 2/3. So we can kind of redraw this free body diagram in terms of mg here. N is equal to mg. F is equal to 2/3 of mg. Okay, amazing. So we're being asked to find the resultant force here acting at A. The resultant force here is essentially like adding these two forces together. We've got mg acting up, we've got 2/3 of mg acting to the right. One way we could understand that is it looks like this, where we've got 2/3 mg acting horizontally, mg acting vertically. We're being asked to determine the resultant force here, which this shouldn't be a shock. We can solve this using Pythagoras' theorem, which is going to look something like this. So we'll take the square of 2/3 mg, which we could write as 4/9 of m squared g squared, plus the square of this, which is also going to be m squared g squared. We can factorize the inside of that root there, so we can say m squared g squared brackets, well, it's going to be 4/9 plus 1, which is going to be 13/9. Okay, we can then simplify here. This m squared g squared can root to mg, and this 13/9 can simplify to, well, square root to 1/3. That's the 9th there rooted. Root 13, that's the 13 obviously rooted there. So we can say F R is equal to 1/3 mg root 13. That's what we're looking for there. Part E then. So part E is stating in a new model, the rod is modelled as being non-uniform with its centre of mass closer to B than it is to A. A new value for S is calculated using this new model where tan of theta is equal to 3/4. The only thing to note really when it says that is that the geometry of the problem hasn't changed, right? So effectively theta hasn't changed here, and we're dealing with the same triangle. State whether this new value for S is larger, smaller, or equal to the value that S would take using the initial model. Give a reason for your answer. So the idea in this problem is that this weight force here has moved over to the right. Your intuition should say that S is going to get larger here. We can't just use our intuition though. We have to kind of give a rationale. We have to give a reason. So the reason here is effectively that we have at least about A. If you take the moments about A, like we did for part B, you have one moment acting clockwise, which is our mg, our weight here, and you have another moment acting anti-clockwise, which is this normal reaction here. The idea is that the perpendicular distance to this weight force here has increased. So mg has moved over to the right. The perpendicular distance from point A has increased, but the perpendicular distance for our anti-clockwise moment, our normal reaction at point B, has remained the same since the geometry of the triangle has remained the same. So our perpendicular distance for our clockwise moment has increased. Our anti-clockwise moment must then also increase. Since the perpendicular distance hasn't changed, the force acting there must increase. Okay, so we can describe that like so, and I've written this down in my notes already. So I'd say S is larger since the clockwise moment about A has increased, while its vertical distance from the point has remained constant. That's how I'd word it personally. Okay, so those are our solutions. If you have any questions or comments about that problem, please feel free to leave them down in the comment section down below. Otherwise, thank you very much for watching.